Okay, what's left? You may be asking yourself. Exam 4 is next Friday. I'm pretty sure that's right. Friday, 5/6. And that's going to cover everything up through Monday's class. And then we'll be done with new material. You know, up through next Monday's class. No. Yes. And it's cumulative. And then we have the makeup exam. That's optional. That's also, you can think of that as just a new version of exam 4. And you can take that to replace the score on any one of your exams. I will get your exam 4 scores up by Saturday morning. So by Saturday morning, you'll be able to know where you stand with all your exam scores. But I don't know. I'll do my best to get done with the other stuff, but I have kind of a big pile of grading. But yeah, that's a cumulative test, and I also would be willing, I don't think I'm going to do this in the future, but this semester only, if you score better on exam 4 than any of the first 3 exams, and you don't want to take the makeup exam the next week, you want to be done with tests, I'll just replace your lower score with your exam 4 score, okay, since it's also a cumulative exam. You know what I mean? So if you got, like your tests were percentage-wise like 90, 90, 70, and then you get a 85 or a 95 or whatever on exam 4, I'll replace the 70 with that, and then you'll be done. But you can't replace 2, so that'll only be if you don't want to take the makeup test the next week. Yep.
When is the makeup test?
That is when our scheduled final is, and I don't remember what that is. Okay, now I'm less confident in yeah, or possibly Wednesday.
It might be August 3rd.
Okay, I'm going to leave that blank then for now, but I'll find that out. But it's at the scheduled finals period. Yes. He wasn't probably even there yet. And so somebody in dynamics asked me to clarify by saying, so you're saying the only reason we should take the makeup exam is if we're not happy with how we did on exam 4. And that is correct. That's a nice, succinct way of saying it. Yep.
So if I have 2 tests that I'm not generally okay with, I do good on 4, it replaces one of those, and then for the finals week, I can also?
No, just one. I don't. I'll look that up. And then we have one more problem set, in quotes, because it's not really much of a problem set, but it's something you have to turn in. So what that is, I'll give you the assignment right now, but I'll put it on D2L too. Wow, look at you. Getting married today?
No, getting divorced.
Oh, okay. They're both exciting times in a man's life.
New chapter.
Yeah, exactly. So the last problem set, in quotes, is I want you to turn in an outline of all the topics that we've done in the class. With all the significant equations included, in the appropriate place in the outline. Don't do that. It has to look sort of nice, and but I mean everyone should get full credit on that. I don't know, like probably somebody, maybe Travis, will get less than full credit for it, but most people will get full credit. It's just this is something that it's going to help you. It's going to help you get ready for the cumulative test. It's going to help you retain this stuff later. So I'm just trying to make you do this.
You have to try really hard to actually not get points for this one.
To lose points?
To actually not get, to lose points. You have to try really hard.
You won't have to try that hard, but I mean, yes, right. It should not. It should be easier to get full credit than on the other ones. Do you have a question?
Just another thing of just because we didn't have any more than one problem set at the beginning of it.
We have two, right?
No, one.
Oh, shoot. Well, that was an oversight.
Can we skip covering the matrix review that we did in the very beginning?
Skip the matrix review.
Yeah, and the outline.
Why were there a lot of equations?
Well,
She
she
doesn't
wanted an
like to-
outline of all the
She
topics
doesn't like
we
to write,
covered.
that's why. Probably.
Technically, we covered it, but it wasn't really.
I think it should be in your outline.
Okay.
Okay, well, yeah, so I guess we have two problem sets. So one of them's this. Any other questions?
So we have to do better on exam 4. We can't try it.
If you tie, I'll also replace the score with exam 4. But if you get a lower score on one of the makeup ones, I won't like reduce any scores. You know what I mean? So it's no risk to doing the makeup thing, but yeah.
Wednesday, May 11th at 2 p.m.
Oh, thank you. That was the one day that you didn't think. Wednesday, 5/11 at 2 p.m. Oh, that's what time it is right now. So that's easy to remember.
Is it true that if we're going to get 100% on exam 4, then we don't have to retake anything because you're going to...
Yes, that is correct. If you get 100% on exam 4, there's no reason to do the makeup.
So basically you're going to replace your lowest score with 100%.
Right. So let's do the problem that I said we were going to do last time. Bless you. So we have this cantilever beam. And it has a distributed load of 20,000 newtons per meter. And it's 1 meter long, and there's an additional support at the end. So this is statically indeterminate because if you remove that roller at the end, this would still be statically determinate. That doesn't mean that it would be a good idea to put this structure together without that roller there. You know what I mean? That roller serves a good physical purpose to keep this from getting ripped off the wall, but it's statically indeterminate because the roller's there. And Young's modulus is equal to 200 times 10 to the 9. And the area moment of inertia is 1.0 times 10 to the minus 7. And that's Yikes. Ah! Holy moly.
Let's see what you.
What happened? Okay. That's meters to the fourth. What are the reactions? So first, it's pretty easy to see with a simple problem like this, that it's statically indeterminate, because you can see that, like, this problem, you could do the statics if that roller was gone. So if there's an extra joint, it's statically indeterminate. But if you had a complicated machine or combination of structures, a combination of members connected into a structure, it's a lot harder to spot. And so your first approach is to try to do the statics. And how do you know if it's statically indeterminate? You just don't have enough equations to solve for all the variables. So in that spirit, so the statics of this, we have a force vector Ra, a couple Mr, and an upward force Rb. And a total force of 20,000. So Newton's second law says Rax, Ray plus 0, negative 20,000 plus 0 Rb is zeros. So Rax, nothing's going on there. But Ray plus Rb equal to 20,000 is a useful equation. And then we'll go to the moment equation. Mr minus 10,000 plus 1 times Rb is equal to 0. And that gives us another useful equation that says Mr plus Rb is equal to 10,000. Okay, so now all we have to do is solve that system of equations, and then we're done. 1, 2, no! So that's how it comes about that's how you discover that something's statically indeterminate. Okay, so now we have to use constraints at the two joints. And so that's statically indeterminate because we have two equations. Well, let's think of it as, two equations for 1, 2, 3 variables. Damn it. Okay, so now we're going to use deflection and require that V is equal to 0 at x equals 0. V prime is equal to 0 at x equals 0. And V is equal to 0 at x equals 1. Okay, so does anyone have any questions about how I chose those requirements? That says that because there's a roller here, this thing can't move. And the fixed joint requires saying that it can't move, and also at that point its rotation is locked in by the couple at the wall. So it has to be horizontal for an infinitesimal distance outside of the wall too. Yeah, let's do it. That's the attitude I like. I bet Dan was like, do we have to? Nothing. Okay, so cut one. How many cuts do we need? Yeah, just one. Between 0 and 1. Well, we know there's no x component to the force, so I'm just going to write this as RA, Y, and MR over here. And then the distributed load is 20,000 newtons per meter, so we know that's just a downward force of 20,000 x at the midpoint. And then we have the tension, shear force, and bending moment. Newton's second law says 0 RAY plus 0 negative 20,000 x plus t negative v is 0. So t is equal to 0. And RAY minus v, what am I doing? Why would I do that? V is equal to RAY minus 20,000 x. And then the moment equation says MR. This has a moment arm of x over 2, so minus 10,000 x squared plus m minus Vx is equal to 0. So we want to solve for m is equal to negative mr plus 10,000 x squared plus Vx and so we get negative mr minus 10,000 x squared when we combine the two x squareds plus RAY times x, and that's it. Okay, and that's valid over the whole beam. The deflection equation says V double prime is equal to 1 over EI times the bending moment. So that's 1 over EI times all of this stuff. Negative MR minus 10,000 x squared plus RAY times x. Integrate this once and you get V prime is equal to 1 over EI times negative MR times x minus 3 repeating times x to the third plus RAY over 2 x squared. And then there's one more thing we need. Yeah, the constant of integration. Call that C1. and then integrate this one more time, and the deflection is 1 over EI times negative MR over 2 times x squared minus, what's 3 divided by 4?
833.3
Okay, minus 833.3 repeating x to the 4th plus RAY over 6 to the 3rd plus C1x plus C2. So our first requirement, we're just going to go through, we have these 3 requirements for the deflection. The deflection has to be 0 at x equals 0, the slope has to be 0 at x equals 0, and the deflection has to be 0 at x equals 1. We're just going to go through those one by one. So first, deflection is equal to 0 at x equals 1. V is equal to 1 over EI times 0 minus 0 plus 0 plus 0 plus C2. So C2 has to be equal to 0. And now we can update our function for V. Question?
You did at x equals 0.
Oh, I did, yeah, sorry. It's hard to talk and think. Okay, so this is the one at x equals 0. And let's update our function for V. V now is equal to 1 over EI times negative MR over 2 times x squared minus 833.3 repeating x to the 4th plus RAY over 6 x to the 3rd plus C1x. And there's no C2 anymore. And now we're going to go to the requirement that V prime is equal to 0 at x equals 0. Well, we already, on the way to getting V, we came up with an expression for V prime. All of the terms in here have x's multiplied. So if, what? So right. So V prime is equal to 1 over EI times, I forget how many zeros there are in here, but a few, and then plus C1. So C1 has to be equal to 0. And now I'll update this function. So our most current expression for the deflection is 1 over EI times negative MR over 2 x squared minus 833.3 repeating x to the 4th plus RAY over 6 times x to the 3rd. And now our last requirement is that V is equal to 0 at x equals 1. So we'll plug 1 in for all these x values, and you get 0 is equal to 1 over EI times the quantity MR over 2 minus 833.3 repeating plus RAY over 6. So now we can use this expression as our third equation in our system. Multiply both sides by EI, and you get that negative MR over 2 plus RAY over 6 is equal to 833.3 repeating. So that's our third equation. And now we have three equations for three unknowns. So let's calculate this. So here's equation 1, 2, and 3. Here's variable 1, 2, 3. I'll put it in the order RAY, MR, and RB. Yeah.
We solve for shear, right? Internal shear?
Yeah.
But then that does come into play for the moment, huh?
It comes in with the moment. That's right. That's all. But yeah, for the for the deflection, you do it all based on the internal moment. So we haven't done any macroscopic deformations that like explicitly use the shear force. But yeah, the bending moment and the shear force are closely related through that derivative relationship. Okay, so what does the first equation say? Roman numeral 1 up here. It's a long problem. RAY plus RB equals 20,000. So one of those, and the constant is 20,000. The second equation says MR plus RB equals 10,000. And the third one says negative 0.5 MR, 1 over 6 RAY. What's 1 over 6? 0.16 repeating? Okay. And then the constant is 833 and 3 repeating. Can someone solve that system?
I got RAY equals 12,500.
Okay.
MR 2,500.
Okay.
And RB is 7,500.
Okay. Sounds okay. Newtons, Newton meters. Yeah, I would like if you put units. I'd like if I did it too. So, yeah, that's cool. So, now we have this problem where you'd think the loads could be distributed in any way, but because of rules of how the deformation happens, we figured out how they're distributed. That's the idea of statically indeterminate systems.
So if you had the same type of problem, but you, instead of one roller, you had 2 or 3, you would solve the same way as you did right now, except, well, it's going to take you longer.
Yeah, if you had more of them. I assume you could do it the same way, yes. You would have more constrained equations, but also more variables. So yeah, if you had 4 rollers along the bottom to support it, at each one of those rollers, the deflection would have to be equal to 0. And so, but you'd also have all those additional forces from the rollers. And so in the end, you'd get a system of a lot more equations and a lot more variables that you could solve.
So it's like coming full circle to, like before going to internal loads, it didn't seem like you'd ever use them to
Uh-huh.
solve
Oh, yeah, right,
external loads.
right.
So say we wanted to know the deflection at the midpoint, we
Yep.
can just plug it into the V.
That's right. We have the function. So now for any x value, you can find the deflection. And notice that, so do these values depend on the material? Well, in this case, we saw that it doesn't depend on the material at all because that EI just canceled right out of it. It didn't. We would have gotten the same answer no matter what these are. But then if you want to find out how much it's deflected at the middle, that EI is going to be important. And if this is made out of rubber, you'll get a very different answer than if this is made out of steel. Also, don't do calculations with rubber with any of this stuff. Because the deformations get too big. And also because, 2 reasons. The deformations get too big too fast. And also, the relationship between stress and strain is never linear for rubber. If you look at its stress-strain curve, it doesn't have any linear region.
For this class, though, like you can figure it out if you use other things too.
Yeah, that's right.
Just calculations. Don't blame it.
Yeah, right, exactly. Yeah, I don't have anything else to say.
So yeah, a few more times.
Yeah, I could. Any other questions? All right, let's start the last topic. So that stuff you could combine all of the different. You could combine elongation, deflection, angle of twist, all into one big statically indeterminate problem. You just do all of them step by step. Superposition holds. So whatever your total deformation is just the sum of the individual deformations. And so you'd break it up into pieces the same way that we did when we were looking for, what happened to the free end of a beam that was cantilevered to the wall. Okay, so the last thing we're going to talk about is column buckling. And the idea is at what load P do you have to worry about this thing collapsing? So what's the smallest value of P that risks collapse? And we're going to think about a few different ways that the ends can behave. I'm going to always draw it horizontally because that's how we're more accustomed to thinking about this. So I'm going to draw it like this. And the first requirement for the ends are going to be that we have pin joints at both ends. Let me draw that a little differently. let's think of this as a roller over here and a roller over here. And we're talking about loads P this way and P this way. And we're looking for, so the question that we're answering now is very different than the question of what force in the opposite direction will make this thing rip apart. Okay? We're not asking that question here. We're just asking at what point are we in danger of this bulging up and smashing together. Okay? So this is only a compression related thing. Okay, so first of all, do you understand the distinction between what we're looking for here and versus, like, what's the difference between that and like a tensile test where you're seeing how hard you can pull on something before it rips? So what this is going to do is, here's how it's going to fail. This is an exaggeration of the deformation. But at some value of that compressive force P, any little bulge out that this material makes, it becomes unstable, and the force is enough to push it out into this big deformation, and that big deformation is enough for this to break. Okay, so how can we figure out what that critical value of P is?
Is this type of thing worse only solid? For solids are also hollow tubes. If you're talking about columns.
Yeah, this also works for hollow tubes. Okay, so think about just a part of this column. And I'm drawing it with the deflection happening downwards, so this distance would be negative v. Statics says if this is the part we're isolating, this is a free body diagram, this load has to be P for this to be in equilibrium. And those two forces can't be alone for this to be in equilibrium, because what would happen to this object? It would spin. So we need a bending moment applied by the material that we've left off on the right to this to keep it from spinning. So what direction would that bending moment have to be acting, the way I have it drawn? One of those is definitely right. I'm going to go with counterclockwise, because these two forces would make it spin clockwise, and so it has to be counteracted by a counterclockwise couple. So now you can sum the, think of rotational Newton's second law. What we have is that negative p times the deflection. That produces, so p times the deflection produces a clockwise moment. So if we're adding up counterclockwise moments, it's negative pv. And so p has to be equal. Let me write this a little differently. So let's think of so what's the moment produced by this couple p and this distance v? So that would be negative PV, right? Yeah. Okay, so negative PV. Plus this bending moment has to be equal to 0. And that bending moment this comes directly from our deflection analysis. That bending moment has to be equal to, I'm getting a negative sign here, I shouldn't. It should be equal to EIV double prime. Okay, well, I'm gonna have to find this later, but somewhere either this should be positive or this should be negative, and these two together give us this equation. EIV double prime plus PV is equal to 0. And that's the starting equation for this buckling analysis. So you can think of this as a differential equation that says V double prime plus P over EI V is equal to 0.
How come the moment is positive?
I don't know. I'll have to think about that later.
Should it be negative?
Which the M?
Oh, I think, so if V is negative,
Mm-hmm.
right, and then the moment is also negative, those two negative sides would cancel. So it would just be PV.
So V would be, you're right. Yep, you're right. You're exactly right. So this should be positive. This should be positive. Okay, so we start with this differential equation. You've seen an equation like that probably before in Physics 1, at least briefly. Anybody know what the solution to that looks like, generally? To this differential equation?
You gotta do the chart probably.
The what?
The characteristic polynomial. No?
No, we don't have to do that for this relationship. If you have a second derivative of your dependent variable plus some constant times your dependent variable. The solution is a sine and cosine solution. So your general form is like v of x is equal to some constant times the sine of square root of p over ei.
Yeah, you get that from doing that. You do that characteristic polynomial now,
Uh-huh.
and then like that one's in it. You can't just like factor it.
Uh-huh.
So you use the quadratic formula. I think you get like an I in your answer,
Oh, okay. Okay.
and then you like it's weird how you apply it.
Okay, yep. Right. Okay, so this is the general form. And then the function for our specific case, for each specific case, the function v of x comes from applying boundary conditions and those boundary conditions come from the joint requirements at the ends. To the general solution. Okay, so for example, the joint requirements at a pin, V has to be equal to 0. At a fixed joint, V has to be equal to 0 and V prime has to be equal to 0. And so everything that we're going to build up from that general solution comes from applying these requirements and using those to solve for the constants A and B. Okay, and then solving for, eventually we're going to solve for this load P to find the critical value of, that's going to cause buckling. But these boundary conditions, notice, that's very similar approach to deflection problems. We come up with this general solution, and then we look at what kind of deflections the joint allows in order to solve for our constants that are unknown. Okay, any questions about that? So next time, the one that I'll start with will be the one that I drew up here, where we have pin joints at the two ends. And so all we know is that the deflection is equal to 0 at this end and deflection is equal to 0 there. And then we'll go from there to other combinations of joints.
Can you scroll up all the way?
All the way?